Good morning, ladies and gentlemen, and welcome back to AP Chemistry with Mr. Kenton. We're going to continue by really diving into our first section of Unit 1. The video I posted yesterday was a review and kind of a summary of some skills and some understanding that we need to have moving into Unit 1 and the rest of chemistry as we go about and embark on our review journey together. And so the first topic that we're going to look at is the mole and molar mass. Now, in order for us to properly understand the mole and molar mass, we've got to talk about some differences in terms of different units that we encounter and why that's important. And so you've got here this idea of molar mass versus atomic mass. And so I want to start by talking about atomic mass, and then I'll move into molar mass. So atomic mass and molar mass, they are measuring very similar quantities, but it's at the level at which they're measuring them. And so atomic masses are going to be dealing with things that are at the atomic level, that microscopic and that atomic level, okay? And so when we think about atomic mass, the thing that should kind of come to your mind is the use of isotopes. Right? So when we did original chemistry, when you guys were taking honors chemistry, you guys had to do a lot of that practice where we would give you mass numbers, like for example, for carbon, carbon 12 versus carbon 13 versus carbon 14, right? And you guys were asked to determine how many protons, neutrons, and electrons do you have, right? Well, that atomic mass, the carbon 12, 13, and 14, is telling you something about the mass of that individual isotope, okay? So your atomic masses are always whole numbers because you don't have partial numbers of protons and neutrons, okay? And so in order to come up with a scale and measure the masses of protons, neutrons, and electrons, that's where chemists use AMU, or atomic mass units, okay? Now, atomic mass is important because it allows us to determine the average atomic mass. Now, again, you can see here, we're using those terms differently. Average atomic mass is different from the atomic mass. And just to clarify there, the atomic mass is always a whole number, right? So that's your carbon 12, that's your carbon 13, that's your carbon 14. But your average atomic mass is going to take into consideration the different isotopes that you have, so carbon 12, 13, and 14, and how often that those isotopes are found in nature. Now, when you think about this, when we think of what's the average atomic mass of carbon, we would probably go to and say, well, it's on the periodic table. That's that 12.01 number. And that's right. That is the average atomic mass for an atom of carbon. Okay. Now, let's shift there, right? So there, atomic mass and average atomic mass has been dealing with at the particle level. Well, molar mass takes us out of that particle level and moves us into the macroscopic level, into something that you and I can relate to much more readily, right? And so the molar mass is going to be the mass of 1 mole of a substance. And if you're remembering, 1 mole is 6.02 times 10 to the 23rd of whatever particle you're dealing with. So if we're thinking about this and making that connection, when I have 6.02 times 10 to the 23rd, let's say particles of carbon, that means that I should get a very specific mass because that's 1 mole. And that mass of 1 mole of carbon is 12.01, right? So we can see that there are some similarities between molar mass and atomic mass, but there's definitely some big differences, okay? Let's see here. And it asks you to correctly use the following terms in a sentence. You've got molecular mass. Remember, molecular mass is going to be used to describe the mass of a molecule, something that is covalently bonded to other substances. Formula mass, that's going to be used to describe the mass of something that has ionic bonding. So something with ionic bonds, we would say that it has a formula mass. And then atomic mass, as we've stated earlier, that's going to be the mass of an individual atom, okay? And again, there are those definitions. Atomic mass is going to be the mass of one atom individually. Molecular mass is going to be the total mass of all of the atoms in a molecule. And your formula mass is going to be the mass of a unit cell in an ionic compound. Okay, so if you had the smallest particle of a molecule, smallest particle of a formula unit, that would be your molecular masses and your formula masses respectively. Okay, and that should be pretty straightforward. Now, that leads us into our mole. I mentioned the mole previously. Let's make sure we're okay with that. Now, this is based on the work of Avogadro, hence why we have Avogadro's number. And so Avogadro came up and developed this idea that the molar mass is going to be the weight of 1 mole of an object. Now again, that number, 6.02 times 10 to the 23rd, molecules, atoms, electrons, protons, ions, formula units, whatever we're dealing with, when you have 6.02 times 10 to the 23rd of it, you have a mole. And I like to think of the mole like some other forms of measurement and measuring quantities. And the one that is most common is like a dozen. Because when I say a dozen, everybody automatically knows that I'm talking about 12 of whatever object I'm referring to. And so for a chemist and for us, when we say a mole, what we should immediately think to is, okay, I have got 6.02 times 10 to the 23rd of whatever particle makes up this substance, right? And again, that's going to vary depending on the type of substance, whether it's an element or a compound that you're dealing with is going to determine the type of particle that makes it up. Now, for example, you've got 1 mole of aluminum is going to contain 6.02 times 10 to the 23rd atoms. Okay, it doesn't matter what substance we're dealing with. It's 1 mole is always going to contain that number, 6.02 times 10 to the 23rd. For aluminum, because it's an individual element, that's going to refer to atoms. Now, if we want to take that further, what that's communicating to you is that the mass of 6.02 times 10 to the 23rd atoms should be equivalent to 26.98 grams. Now, if you look at your periodic table, that's the mass that's found on the periodic table for aluminum. So that mass of atoms, 6.02 times 10 to the 23rd, is going to have a weight, or a molar mass, of 26.98 grams, right? Calcium chloride, for example. Now, there is an error there. That should say 6.02 times 10 to the 23rd formula units, not molecules, okay? Because molecules refers to covalently bonded substances, and calcium chloride is not covalently bonded. So that means, if we're thinking about this in terms of that molar mass, if you have 6.02 times 10 to the 23rd formula units of calcium chloride, that means that you're going to have a molar mass of calcium chloride that's going to be 110.98 grams. So if you take all of those molecules, or excuse me, formula units, 6.02 times 10 to the 23rd formula units of calcium chloride, that would have a molar mass of 110.98 grams, right? But again, it still contains the same number of particles, but it does have a different molar mass, right? And think of that kind of like the idea that you can have a dozen bricks versus a dozen donuts, but the dozen bricks is going to be heavier than the dozen donuts. The bricks wouldn't be nearly as tasty, though, as the donuts. And last thing here with the molar mass of an element is found by looking at the atomic mass of the element on the periodic table. That's exactly what I did for aluminum, and that's how I got that 26.98 number. And then if I have a compound like calcium chloride, I take the masses of every substance or every atom, add them together, and that gives me my molar mass. Now for calcium, that was the 40.08, and then the 35.45 times 2, which gave us that 110.98. Now that we have an understanding of the mole and how it is useful to us, the mole allows us to be able to convert between different types of units, right? And so, like in this flow chart, let's say that you're given grams of substance A. Well, what you can do is you can use the molar mass of substance A to get you to moles of substance A. And what you would do is you would take the grams, divide it by its molar mass, and that'll give you the moles. And then if you've got a balanced equation, you could use the mole ratio, the coefficients in that balanced equation to go from substance A to substance B. Now you're in moles of substance B. Then you could use the molar mass of substance B, so multiply it by the molar mass to get grams of substance B. And of course, we've seen this. You can do this with volumes, with liters. You can do this with particles. You can do this with molarities. There are all different types of calculations we can do with stoichiometry by using the mole. And that's why the mole is such an important piece for us. Okay. And just looking at an example of a mole conversion, let's say we wanted to know how many chloride ions are in 20 grams, 20.0 grams of magnesium chloride. Now, because I like to kind of tie in information that we've already gone over, think about this. How many significant figures does 20.0 grams have? Hopefully you paused and took a look at that. That should be 3 significant figures, so we know that our answer should have at least 3 significant figures in it. Well, how would we go about solving this and using mole conversions? Well, let's start with our 20 grams of magnesium chloride. So that 20 grams of magnesium chloride, that's 20.0 grams of MgCl2, that's our correct chemical formula. We would then use the molar mass of magnesium chloride, so that's 95.2 grams of magnesium chloride in 1 mole. Now, it's not asking us about how many formula units of magnesium chloride do we have. It asks specifically for chloride ions, right? So that's an important piece of information. Now, when you look at that, within 1 mole of magnesium chloride, we should be able to communicate, because there's that subscript of 2 here beside chlorine or chloride. That means that for every 1 mole of magnesium chloride, I have 2 moles of that chloride anion, right? And so that would give me the moles of chloride ions that I have, but it doesn't ask me for moles of chloride ions. It asks me for how many chloride ions do I have. So then I need to take it a step further, and I know for 1 mole of chloride ions is going to be equivalent to 6.02 times 10 to the 23rd chloride ions. Now that I have my setup, you would just multiply that in your calculator. You got 20 times 1 times 2 times 6.02, 1 times 2 times 6.02 times 10 to the 23rd. And you're going to divide that by 95.2. And so you would find that you would have 2.53 times 10 to the 23rd chloride ions in that sample of magnesium chloride. Okay, hope that was helpful. What I want you guys to do, which you should have already done this, those are the questions that we've answered. So adding into that, we've done these questions already. You can look back at those and see if you need to work through them. If not, you're good to go, and I look forward to seeing you guys again soon.